process, but which calculates precisely, not like in phenomenological potentials, 3-body, 4-body forces. So this is it. What are the developments? I just show here some results. For instance, the simplest case, of course, is neutron matter, pure neutron matter. This is an approximation. And these are results which are shown here by 2 authors in the interval of 3 years. So lambda is this. For instance, the contribution of 4-body forces, and here is the baryon density, up to nuclear density. The contribution from 4-body forces is just minus 0.18 MeV, so it's very small. So actually, 4-body forces are not important at these densities. And these are results obtained recently. So this is the precision of the calculation, because this is perturbative approach. And we do not have pressure here, but we will get it from the authors. This is the previous calculation of equation of state. So you see, unfortunately, that the precision of this basic type calculations decreases very rapidly with density, and we have problems above nuclear density. So this is my first example of development. So this is the chiral effective field theory. And then I go to relativistic mean field approach. It's completely different, completely different. We have effective Lagrangian for the mean field. No pions appear, because in the mean field approximation, pion contribution is 0 because of the symmetry of the ground state. We have baryons. We have meson fields, we have static solution in the mean field approximation, and we have a puzzle, if we have such a theory, that's an approximation, how to make this relativistic mean field simultaneously consistent with nuclear constraints, which are now quite precise, and astrophysical constraints, mainly 2 solar masses. And there are 2 ways to reach this aim. Way 1, to solve the puzzle, I will discuss it here. Minimal structure of Lagrangian, so minimal structure, just several, mesons, and just quadratic terms with some corrections, but with coupling constant between baryons and mesons, and meson and baryon masses scaled with one field which is here, which is scalar field. You know, Lagrangian density is a scalar, and so the dependence should be on a scalar quantity. So this is one approach, and this is, Dr. Maslov is, I hope, here. This is one approach. Yes, and another approach is to make coupling constants in this Lagrangian, in this theory, density dependent. And this is Stefan Tippel approach and his collaborators. I will very briefly describe what does it mean. So there is also a second way to solve the puzzle, more meson fields. Quartic terms, more mesons, and then you can satisfy these 2 constraints. I will show recent developments in this way. So Kolomiejtsev et al. So just nucleon matter to make things simpler. There is a scalar field. This is so-called sigma meson. Nobody saw sigma meson, but it is something which represents 2 pion exchange, very roughly speaking. So you can make it dimensionless. So this is dimensionless scalar field. And there is an effective coupling constant with some function which renormalizes this coupling constant used previously. And then we have a scaling. So the masses of baryons and nucleons and mesons scale with density according to the linear way of behaving of a scalar field. This is something that comes from nuclear theory, actually, the scaling in dense matter. In this way, we get some, so to speak, flexibility. And it's quite, probably likely that such thing occurs in dense matter. So then Lagrangian is simple as possible. But this scaling is included. Lagrangian is just quadratic in omega field, rho field, and phi field. It's not, I will not enter into details. So this means that equations of motion for these vector fields are extremely simple. They are trivial, actually. They are linear. Yes, and what we have to solve is this equation of motion for the crucial field here, which is the sigma field. And this is the approach of Kolomietsev and colleague, and this approach is quite successful. Yes, and they can include also not only nucleons but also hyperons and delta resonances in their models. They can use various additional features of the model or measurements for hyperons, and they get equation of state, which is as it should be. Of course, it is some tuning inside, and it is as it should be. That is, this equation of state obtained by them is soft rather, so it has radii which are not very large for symmetric nuclear matter and also for neutron stars at densities less than 4 times nuclear density and very stiff. For instance, pure neutron matter is very stiff to get 2 solar masses at high densities. So it is the result of this scaling and of this model. In this way, there is no problem with deltas, no problem with hyperons, provided some range is assumed. Delta and H puzzles that prohibited to get 2 solar masses. They softened it looked like. Here, they are not dangerous. And respecting nuclear physics is satisfied. 2 solar masses constraint are satisfied. Well, actually, there is very low strangeness content at highest masses. So actually, there are nearly no hyperons, only at very high mass, above 2 solar masses. You will see it. So this is the solution. Then another approach is Steipel et al. Density dependence of coupling constant. This is some subtle problems because density itself is not a scalar. But it may be assumed that this is, a square root of a scalar. But this is only in a very special reference frame under the assumption of single baryon fluid. So there are some strong assumptions. There is successful parametrization and everything works. So this is what I call the progress or new development. Results. Here are the results for equation of state here for these various types. So it is Kolomietsev with hyperons, with deltas. Here is Steipel with hyperons, without hyperons. And here are mass-radius relations. So you see, the equation of state is quite flexible. It can get well above 2 solar masses. Hyperons do not kill this feature. This is Kolomietsev here, but you see how these are thresholds. They appear above 2 solar masses, these hyperons. So they have no way to influence very much the mass-radius relation. Yeah. Deltas appear here, but they do not soften much the equation. Somehow they soften, but and this is Steipel. This is DD2, density dependent. So it's very different. There is a difference, 1.5 kilometers in radii for astrophysical masses of neutron stars. You see, at 2.5 densities, nuclear densities, this is the model of Kolomietsev. This is the model of Steipel. So the internal structure of neutron stars is very different here. What structure is true? Measurements will show it. So this is the first development. The second development that I show. Now I ask Mr. Chairman, how much time do I have? Because I want, 10 minutes. It's not much, but still I will survive. So the second point, equations of state with more microscopic approach. So we have baryon-baryon interaction. These are results of quite heroic calculations of Katayama and Sato in Japan. So they use so-called Dirac-Bragner-Hartree-Fock theory, and neutron stars with hyperon cores are shown here. So it is more microscopic than the theory of Kolomietsev. They get two solar masses here with hyperons too. The radii are some 13.5 kilometers at relevant densities. And they find, which is quite interesting, they find that the maximum mass configuration is not very sensitive actually to the model they choose for hyperons and their interaction. Please look at the maximum density here. In baryon density, just 5 times baryon density of nuclei. So you see, neutron stars, if they want to have two solar masses, they do not have huge densities at the center. It is not 10 times nuclear density, as we usually say, but this is here 5 times density in nuclear baryonic number units. So this is the maximum mass. This is the number of mesons they use. It does not depend so much. This is number of baryons. It can be 8, can be 5, depending on the number of hyperons they include. So this is it. Then, how many minutes do I have? Because now I have to be... 5 minutes. Oh, it's, yeah. So this is this new unified equations of state. You see, one of the dreams of theorists is to have the equation of state based on one interaction, theoretically justified interaction, which describes all neutron stars from the surface to the center. So this is unified equation of states. There were developments in the past, and very recently there was a new approach to this problem, and new equation of state was calculated. It has a long name. It is Barcelona, Catania, Paris, Madrid, effective energy density functional. And we have such a new equation of state. It is consistent with nuclear physics, and it is also similar to what existed before. And we have also many new unified equations of state based on relativistic mean field models. This is, for instance, done in the paper by Fortin et al. 9 new equations of state which are relativistic, because the previous one was not relativistic, and there might be a problem in the highest densities with causality. Yeah. So this is what is now. So the choice is much bigger. The choice is much bigger. Consistency with measurements in nuclear physics is better. And these unified equations of state are very valuable for precise calculation of radius. This is what Morgane Fortin will discuss in her talk. And it is also important for the crust moment of inertia. So this set, available set, increases. Now Mr. Chairman will tell me, either will me cut me, and I will just have one more slide and then conclusions. Mr. Chairman? 3 minutes is fine. Oh, the time is flowing not so quickly. So I go to the last development. Here it is. Oh, these are the results, you see, unfortunately, with density. This goes not so nicely. There are some divergences. These new developments, these are unified equations of state. This is for the crust. This is for the core. But still, there are some uncertainties that, of course, persist, and they are even in the inner core. There are uncertainties. But this is what we have. It's much bigger choice. And the last point, I will be really brief, is that we have to remind one thing. If we want to discuss neutron star cores at many times nuclear matter density, we should remember we should remind one feature which is important. Quarks are point-like objects. Leptons are point-like objects. But nucleons and hypers are not. They are finite size. And with increasing density, this finite size can influence, stiffen the equation of state. There is a method to calculate it. This is excluded volume approach. And I have no time to present the effects of this excluded volume, and I just go to the last slide, which are the conclusions. So, just in 1 minute, there are some developments since 2014, the last conference, Physics of Neutron Star, but progress is very slow. But it was always so. Actually, the breakthrough were coming with observations. This is the situation. We have to be modest. Precise equation of state for pure neutron matter can be calculated using this effective field theory, but at subnuclear densities. Contribution of four-body forces is small. No hope to calculate precise equation of state using this beautiful method above nuclear density because of slow convergence. Progress, well, there are many unified equations of state now. There are beautiful equations of state, relativistic, which come from Brussels group also. So this is the progress. There is some scattering of equation of state. Scaling of in medium makes and density dependence of coupling constant makes equation of state more flexible. H puzzle and delta puzzle can be solved. And then there is the rest. And here it is the end. So thank you very much for being so kind to me. Mr. Chairman, this is the end. Yeah.
Yes. We have few questions. Please.
My question related maybe for your last statements. You have shown that, say, hyperons in some equation of state appear above 4 nuclear densities, when the sizes of hyperons are already larger than mean distances. So in what sense can we speak about particle, or are they quasi-particles or what?
Well, it's a fundamental problem, of course. I mean, as I said, the fundamental theory is QCD, but it cannot be used. And it predicts, of course, the finite size of baryons. They are confined to certain, quarks are confined to the volume of baryons. But it's very difficult to calculate. You should remember this when you are looking at the equations of state. But the effect are two effects of this finite size. First effect is stiffening of the equation of state per baryon, but there is another one. As the baryons come closer together, there will be a phase transition to quark matter, most probably. And this finite size will accelerate it. But it's all beyond our theoretical possibilities. I say it, with all modesty. Yeah.
Please.
So one of the important points that you made was this new insight that above 4 times nuclear density, that the equation of state would become very stiff.
It should be.
Yeah, so that was interesting. But is it possible, what I didn't understand was you were also showing some neutron star equation of states where at the center they were just barely reaching above 4 times nuclear density as well.
Yeah.
So is it possible astrophysically to have neutron stars then that don't reach those central densities that are actually quite soft?
I mean, there is clearly a bound on the density of baryonic equations of state, neutron star cores if 2 solar masses are reached. And this is what I wanted to stress. I mean, the density for baryonic neutron stars, should not be larger than, say, 6 in baryon density units. 6 baryons per Fermi cube. It should be 0.6 baryons per 6 nuclear densities. So this is it. In energy density, it should be not more than, say, 8 nuclear densities in energy units, so to speak. Otherwise, your object becomes so compact that it is unstable, and it cannot reach these 2 solar masses. This is something that was discussed in literature, I think. Yeah, so this is it. They cannot be too dense because these 2 solar masses would kill them. Maybe there are 2 branches of neutron stars, one dense, but I mean, it's, we have to use Occam rule, I mean.
Okay, that was basically what I was asking.
Yeah.
Yeah, okay.